Hello everyone, so in this video I'd like to talk a little bit about derivatives of log functions, so how to differentiate them, and then look at a few applications. And the main application is going to be logarithmic differentiation. And here the main idea is to use the fact that logarithms turn products into sums and quotients into differences, and also powers into multiplication. And this makes it way easier to differentiate functions because, for instance, the derivative of a sum is much easier to do than the derivative of a product, and so on. So let's get started. So the first derivative we need to know is derivative of log to the base b of x is 1 over x times natural logarithm of b for x bigger than 0. And if we insert base b equals e into this, then we get the well-known formula derivative of ln x. So log to the base e is just ln, becomes 1 over x because the natural logarithm of e is just 1. Okay, so the second formula is a special case of the first, but we are going to use the second formula way more. Okay, so derivative of ln x equals 1 over x for x bigger than 0. And why is this true? For instance, if y is the natural logarithm, if y is the logarithm of x to base b, we can rewrite that equation as b to the y equals x, right? Just using the fact that these are inverse functions, right? Exponentiation and logarithm are inverse functions. And now we can differentiate both sides of this with respect to x using implicit differentiation, right? So normally the derivative of b to the y would be b to the y ln b, but since we're differentiating with respect to x, we get b to the y ln b times dy dx. And then on the right side, we differentiate the x to get 1. Okay, we solve for dy dx. We get dy dx just moving things over, dividing is 1 over b to the y ln b. Okay, but we remember that b to the y was supposed to be equal to x. So we can get an answer in terms of x, and it's 1 over x natural logarithm of b, exactly as we said, and that's how to get the first formula. So here the strategy is pretty much the same as how we got the derivatives of inverse trig functions, right? We're just using implicit differentiation to move things around and go back to the original function, not the inverse function, which we already know the derivative for. Okay, and as we said, we get the second formula for ln just by using base b equals e. And you can also check, so the slight downside with the first formulas we talked about is that they only work for x bigger than 0. Okay, if we want all x not equal to 0, if we want a formula, then we have to insert an absolute value, right? Because logarithms of negative numbers are not defined. But what is true is that if we look at the derivative of ln absolute value x, then that is 1 over x for all x not equal to 0. So this is going to be really useful later when we talk about integration and finding general antiderivatives, which is reversing the process of derivatives. If we want to find later an antiderivative of 1 over x, then the right answer is going to be ln absolute value x, right? Because this works for more values of x. Okay, so let's look at some simple examples. So just as with trig functions, inverse trig, and so on, we can combine these derivatives with other rules we know, like the chain rule, the product rule, the quotient rule, and so on. So for instance, here, y is the natural log of e to the x plus sine x plus x squared. We differentiate, right? The outside function is ln u, the inside function is this mess. So we have to do the derivative of the outside. So derivative of ln u is 1 over u, evaluated the inside. So we get 1 over e to the x plus sine x plus x squared. And then we multiply by the derivative of the inside, which is this second piece. Okay, so pretty straightforward. But with some other examples, it might be simpler to first simplify using log rules. So for instance, if we want to differentiate y equals ln of x to the 10, then we could jump in and use the chain rule as before, as in the first example, and that would be fine. You will get the right answer. But something that is simpler is to notice that we can use logarithm rules to write this instead as y equals 10 natural logarithm of x. And now we don't have to use the chain rule at all, right? The derivative of ln x is 1 over x multiplied by 10. The derivative is going to be 10 over x. So here, even in some very simple examples where we're not doing anything involving logarithmic differentiation, we're just trying to differentiate some functions, it can be useful to first use the rules of logs to simplify the expression, okay? So just a reminder of what are the rules of logs. So logarithm of a product is the sum of the logarithms, right? Log of xy equals log x plus log y. If you insert base b equals e, you get the same rule for ln, right? So ln of xy equals ln of x plus ln of y. The same with quotients, it's subtraction. So log of x over y equals log of x minus log of y. And log of a power, the power comes out front. So log of x to the n is n logarithm of x. So logarithms, roughly speaking, they turn products into sums, quotients into differences, and powers into multiplying by whatever the exponent was. And we should be careful here. There is no rule for log of x plus y, and there is no rule for log of x minus y, right? So please don't try to write log of x plus y as something, because that will lead you astray. So it's a rule for the product, the quotient, and the power. Okay, so here's a more sophisticated example using these rules. So let's try to differentiate ln of 2x plus 1 to the 5 over the square root of 1 plus x squared. So if we were to just try to jump in and use the chain rule, well, we'd have to use the chain rule, and then we would have to use the quotient rule, and then on each piece we would have to use the chain rule again. So there would be quite a number of steps. So let's, instead of doing that, try to simplify using rules of logs. So we have ln of a fraction. So we can turn that quotient into a difference. So we can write it as ln of 2x plus 1 to the 5 minus ln of square root 1 plus x squared. And then each of those pieces are powers. So we can use the rule for powers to bring out the powers. Okay. So if we do that, we first use the rule for quotients, and then we bring out the powers. It's going to be 5 ln 2x plus 1 minus a half ln 1 plus x squared. Right, and the half is there because square root is power 1 half. And now this is way easier to differentiate because we can just differentiate each piece separately. So if we differentiate the ln 2x plus 1, okay, we have to use the chain rule. Derivative of ln 2x plus 1 is going to be 1 over 2x plus 1 times the derivative of the inside. So 1 over 2x plus 1 times 2. Then we have to times by 5. So we're going to get 10 over 2x plus 1. And then similarly on the second piece, we use the chain rule. We're going to get 1 over 1 plus x squared times the derivative of the inside. So times 2x, but then we have to multiply by a half. So the 2 and the half are going to cancel each other. We're just left with a x over 1 plus x squared. Okay, so here we had, even in an example where we didn't talk at all about logarithmic differentiation, first using rules of logs can make our life way easier if we use them before jumping in and differentiating. Okay, so let's get on to logarithmic differentiation. So here the point is that using logarithms can make it easier to differentiate some functions, even when there aren't already logarithms at the start. So even if we have a function f of x, if it has a lot of products and quotients and powers, even if it doesn't have logarithms to start, it can still make sense to use logs to help us differentiate. So what are the steps? If we have a function f of x with lots of products, powers, and quotients, we could try logarithmic differentiation. So what are the steps? Well, the steps are we write y equals f of x, so y is our function, and we take natural log of both sides, so we take ln of both sides. And then we use the log rules to simplify the products, the quotients, and the powers, as we'll see in a second. So that gets something easier to gives something easier to differentiate. And now we have to differentiate both sides. So on the left, if we took ln, we are going to have ln y. We can differentiate that with respect to x. We get 1 over y times dy dx. And then the right side is going to be something involving x, which we can just differentiate. And then on the left, we have 1 over y dy dx. We just solve for dy dx and replace y by whatever it was in terms of x. So let's see an example of this actually happening. So let's try to differentiate x to the power of square root x for x bigger than 0. And notice we could not do this with any technique we've seen before now, because the basis involves a variable and the power involves a variable. And before we saw rules where the base was a variable, but the power was a constant, right? The x to the n rule. We saw a rule where the base is a constant, but the power is a variable, right? Like b to the x rule. But we didn't have anything where they're both variables. So let's see how to do this, and let's do logarithmic differentiation. So we are supposed to take ln of both sides. So if we take ln of both sides, we get ln of y equals ln of x to the square root x. Okay, now we can use the rules of logs to bring down that power. So it becomes square root of x times ln of x. And now if we just focus on the left, on the right side, it's easier to differentiate. So if we differentiate ln y with respect to x, remember differentiating functions of y, but with respect to x, it's what it would usually be if you were differentiating with respect to y, but multiplied by dy dx. So you're going to get 1 over y dy dx. And then on the right side, it's a fairly standard product rule because now we know how to differentiate ln of x. Right, so if we do that, we get 1 over y dy dx, and then on the right hand side, if we fix the square root x, we differentiate the ln x, we get the first term. If we fix the ln x and differentiate the square root of x, remember square root of x is x to the 1/2. We differentiate, we're going to get a half x to the minus 1/2, which is this second term here. Okay, so this is what we get when we differentiate both sides. And now we want to solve for dy dx. So if we want to do that, we should multiply both sides by y. So we're going to get dy over dx equals y times whatever this was. And then we have to replace y by what it was in terms of x. And luckily, when we do this, we're starting right with our formula for y. So dy dx is going to be x to the power of square root x. Here was the y times whatever we got in the first step. Okay, here there was a square root x, there was a 1 over x. We just cleaned them up into 1 over square root x. Nothing really happened. Okay, and these steps are pretty typical. So it's always pretty much doing the same thing. Take ln of both sides, use the log rules to simplify, differentiate both sides with respect to x, keeping in mind that the left side, ln of y, you're going to have to differentiate implicitly. So it's going to be 1 over y dy dx. And then we solve for dy dx and replace y by whatever it was in terms of x. Okay, so here is the derivative. Not one we would have guessed, right? So it's really important that we do have to use the rule for x to the square root x. We have to use these steps. We can't try to adapt one of the rules for x to the n or b to the x that we saw before. Okay, so here we were assuming, by the way, that x is positive, or y is positive, right? Here, x to the power of square root x, if x is bigger than 0, y will be positive. If we are taking ln of both sides, well, ln of negative numbers don't make sense. So this would only work for y bigger than 0. So what should we do if y is negative? Well, instead of writing ln y equals ln f of x, instead write ln of absolute value of y equals ln absolute value f of x. So this amounts to first taking the absolute value and then taking natural log of both sides. So it's still a true formula. And then if we differentiate both sides from here, remember that the derivative of ln absolute value x is 1 over x. So basically when you do the differentiation, nothing changes because you can use the fact that the derivative of ln absolute value is just 1 over, okay, for all x. So let's try to use this strategy to check the derivative of y equals x to the n. So we've already seen this and we know it should be nx to the n minus 1, but let's check why that's true and see how it works. Okay, so keeping in mind that, for instance, x could be negative and y could be negative depending on what is the power n. So we want to take that into account. So we want to take absolute values first and then take natural logs. So we get ln absolute value of y equals ln absolute value x to the n. So then we want to simplify using rules of logs. Okay, we can swap the absolute value and the power, and then we can bring the power out. So we are just left with n natural logarithm of x. Okay, now let's differentiate both sides with respect to x. So we know the derivative of ln absolute value x is 1 over x. So if we were differentiating ln absolute value of y with respect to y, we would get 1 over y. But we're differentiating with respect to x, so it's going to be 1 over y dy dx. Okay, so on the far left, we're going to get 1 over y dy dx. And on the far right, we're going to get n times 1 over x, so n divided by x. Okay, so when we differentiate, that extra absolute value pretty much disappears. So we don't really have to worry about that. Okay, and now as before, we solve for dy dx, we replace y by what it was in terms of x. So we are going to get dy dx equals y times n over x. Okay, y is equal to x to the n. So we get n x to the n over x, so n x to the n minus 1, which is exactly the same answer that we've already seen, right? So everything makes sense. So remember logarithmic differentiation, take ln of both sides, simplify with rules of logs, differentiate both sides, and then solve for dy dx. And if things are negative, then you have to take absolute values first before you do that. Okay. Okay, maybe one final observation is that right now we have two different ways to compute the derivative of ln x. So we had the way that we just did it using implicit differentiation. Basically, we turned it around, used the rule for the derivative of e to the x. That gave us a rule for ln of x using implicit differentiation. So we can do that, it's 1 over x. So if we want to compute, say, f prime of 1, that's going to be 1 over 1, it's going to be 1. Or we could go back to the limit definition. So let's see, and if we do it these two ways, they have to give the same answer. So let's see if that tells us anything interesting. So for instance, if we apply the definition, f prime of 1 is going to be the limit of f of 1 plus h minus f of 1 divided by h. Sorry. Right, so f of 1 plus h minus f of 1 divided by h. We let h go to 0. Okay, so here f of x is ln of x. So we're going to get ln of 1 plus h minus ln of 1 divided by h. And then if we can simplify, because ln of 1 is 0, and if we rewrite dividing by h as times 1 over h, we get 1 over h times ln of 1 plus h. And then we can bring inside that multiplication into the power for reasons that will be clear in a second. So this becomes ln of 1 plus h to the 1 over h, okay, which is not an easy limit at all. So why is this not easy? Well, as h is going to 0, the inside is going to be a number which is a little bit bigger than 1. But as h goes to 0, the power is getting larger and larger and larger, so it's going to infinity. And depending on which is happening faster, we either get 1. So for instance, if the power stayed fixed, but the inside was going to 1, then we would have 1 to some power, we would get just 1, regardless of what the power was. If the inside was fixed, if we had 1 plus h, which is a little bit bigger than 1, the power is going to infinity. So we have something like 1.1 to the power of something going to infinity, we will get infinity. So depending on, if you fix 1 at a time, it's either going to 1 or it's going to infinity. But we're not fixing 1 at a time, right? They're both changing at the same time. So this is an indeterminate limit of the type 1 to the power of infinity. So this is not something easy. Anyway, let's let's continue. So if we go back to using our rule, f prime of x is 1 over x, okay, f prime of 1 equals 1. And now we know that these are both the same, right? So this limit has to be equal to 1. Okay, but I don't care about having this ln here, so let's take exponential of both sides. So if we have 1 equals the limit of this thing involving ln, if we do e of both sides, e to the power of 1 is just e. E to the power of ln, remember e and ln are inverses, so they are going to cancel each other out. So we just get e as the limit as h goes to 0 of 1 plus h to the 1 over h. Okay, so remember we said that if we fix one or if we fix the other, then it could go to 1 or it could go to infinity, but in reality, they're both varying at the same time. So there is this delicate tug of war. And actually, this limit is e. So this is a limit that's worth knowing. And if we write h equals 1 over n, then instead you can write this as e is the limit as n goes to infinity of 1 plus 1 over n to the power of n. And here it makes it a little bit clearer what was that trade-off we were talking about, right? So on the inside, we have something a little bit bigger than 1, but on the outside, the power is getting larger and larger. Okay, what happens? Well, it depends on how large things are getting. In this case, the limit is e. So this is quite a famous or worth knowing limit. Okay, so just to recap, we saw how to differentiate ln of x, right? That was 1 over x. To differentiate log to the base b of x, that was 1 over x ln b. Sometimes if we want to insert the absolute value, for instance, the derivative of ln absolute value x is 1 over x for all x not equal to 0. We saw logarithmic differentiation, where the steps were to take logs of both sides, use log rules to simplify, differentiate both sides with respect to x, and then solve for dy dx. And that can be useful if there are lots of powers or products or quotients. And then at the end, we saw this new limit involving e. Okay, thanks everyone. See you next time.